American history records the Toledo War, a rare instance when two sovereign states took up arms against each other. Ohio and Michigan, after 20 years of sporadic fighting, finally had their differences settled for them. In 1837, the United States Congress awarded the hotly contested Toledo Strip to Ohio, and at the same time, ceded the western portion of the Upper Peninsula to Michigan as a consolation prize for the loss of the Strip. The unpopularity of the decision by Congress might well be summed up by a newspaper editor of the time.
Ha! I wonder why they didn't give us a slice of the moon. It would have been more valuable. Agreed.
How wrong he was. For only 4 years later, in 1841, copper was discovered in the Upper Peninsula. For a period of 36 years, from 1847 to 1883, Michigan produced 50% more copper than all of the rest of the country. 3 years later, one of the richest iron ore deposits in the world was discovered. The opening of the Sioux Canal in 1855 greatly stimulated iron mining, so much so that for 17 years, up to 1901, Michigan was the leading iron producer in the world. And its virgin forests made it the nation's greatest lumber producer in the country for a period of 20 years, from 1870 to 1890. After Chicago was leveled by the Great Fire of 1871, almost all of the lumber for the city's reconstruction came from Upper Peninsula forests. And the future held the promise of a tourist's mecca of unsurpassed beauty. Historic Mackinac Island, the pictured rocks, Lachino Islands, Tequamanen, largest waterfall in the Midwest, beautiful streams and lakes teeming with game fish and waterfowl, and virgin forests abounding in wildlife. But unfortunately, separating this veritable paradise from the lower peninsula was a 4-mile water barrier. The Straits of Mackinac, connecting Lake Huron and Lake Michigan, each capable of stirring up some pretty rough weather. No matter which lake was responsible for the storm, the Straits took the brunt of it. The dedication of the Brooklyn Bridge in 1883 challenged the imagination of northern Michigan citizens. The Grand Traverse Herald was the first to advocate a Straits crossing. If there is to be a great through route from east to west through Michigan, there must be a sure and permanent crossing at the Straits. Then it concluded, shall it be a bridge or a tunnel? A bridge, said a St. Ignace department store owner. His ad featured a pen and ink drawing of the newly opened Brooklyn Bridge with the caption, "Proposed bridge across the Straits of Mackinac." These were the opening guns in a 70-year struggle for a Straits crossing. Starting in 1921, a number of plans for a Straits crossing were proposed. Among the first was a unique suggestion for a submerged or floating tunnel to connect the peninsulas. Soon afterward, another engineer proposed an elaborate island-hopping plan for a series of causeways and bridges, beginning at Sheboygan, leapfrogging to Bois Blanc Island, then across to Round Island, over to the west tip of Mackinac Island, and a final hop across the deep channel to St. Ignace. The complete roundabout crossing totaling 24 miles. While nothing came of these plans, the growing demand for a better Straits crossing facility did bring some indirect action. The state of Michigan started a ferry service in 1923, supplementing the old railroad boats that had been in operation since the horse and buggy days. The ferries operated between Mackinac City, where all the important lower Michigan roads terminated, and St. Ignace, where all upper peninsula roads converged. The shortest route across the straits would obviously be a beeline between these two terminals. Several plans to bridge this direct route were suggested, but the lack of vision or confidence seemed to frustrate every effort. In 1940, the ferry fleet was doubled, but still failed to keep pace with the increasing traffic. Interest in the bridge rose again. This time, a leading engineering firm recommended a double-span suspension bridge across the straits. This plan actually reached the action stage, and a causeway was built from St. Ignace, 4,200 feet south into shallow water. Then came Pearl Harbor. The double suspension bridge was chalked right off the drawing board. But with the causeway, the bridge enthusiasts had finally established a beachhead. This causeway stood unused for 16 years. It wasn't until 1950 that the 65th Michigan legislature created a new Mackinac Bridge Authority, headed by Mr. Prentice M. Brown as chairman. In only 3 years, this authority accomplished what had been but a dream for 70 years. One of the first acts of the authority was to engage a group of prominent long-span bridge engineers, including the internationally known Dr. David B. Steinman, destined to design the greatest bridge of his career. After a prolonged study came the report, "Building a bridge across the straits is entirely feasible, both physically and economically. Yes, a bridge that would withstand all the forces of nature, winds, ice, and strong currents." Here are the plans. In the designer's own words, a bridge is merely mathematics brought to life. And here's the wherewithal that brought the mathematics to life. A certified check for over $96 million. Now things began to move. Construction men called this fleet the largest concentration of marine equipment ever assembled for a civilian project. The design called for construction of 34 piers. But where do you begin building a bridge? Where do you get a foothold? Engineers, by survey, established the center line of the bridge. Here was the humble forerunner of the great bridge that was to conquer the Straits of Mackinac. Pier 17, one of the 2 giant anchorages, was chosen as the starting point. With surveying instruments mounted on towers extending down to bedrock, engineers, using triangulation, pinpointed the exact location for Pier 17. Since it was only 88 feet below the waterline, open cofferdam construction could be used. Then on April 25, 1954, the engineers, using their instruments and radio communications, guided the operation of the men on the barges as they lowered a specially designed bracing, which served not only to mark the sides of Pier 17, but also to help support the cofferdam walls during construction. With the bracing in place, piling was hammered all the way down to bedrock, completely boxing in the skeleton framework. Inside the steel enclosure, on top of the bedrock, were thousands of cubic yards of mud, clay, and stone, overburden, which had to be removed to make room for the concrete fill. An endless belt dumped a coarse stone aggregate into the cofferdam from self-unloading ore boats. Merritt, Chapman, and Scott Corporation, the foundation contractor, using the pre-packed intrusion method of concrete construction, piped a mixture of cement, sand, fly ash, and water into the caisson to fill the voids in the stone aggregate, creating a massive 170,000-ton block of concrete. Enough concrete to pave 20 miles of a 4-lane superhighway. And buried deep in the heart of the anchor pier are the huge steel eye bars, which will permanently anchor the cables that support the bridge. Next came the construction of the two main tower piers. The sections for the caissons were fabricated at the Gary plant of American Bridge. They were then shipped to Alpena, Michigan for assembly. Since these were to be sunk over 200 feet below the surface of the water, prefabricated, double-walled steel caissons, 116 feet in diameter, were necessary. Floating the massive caissons to the bridge site was no small chore in itself. It's not difficult to see why someone called these caissons Paul Bunyan's Donuts. Steel four-sided corrals were lowered into position. They would later guide the caissons into place. The caisson, with its cutting edge on the bottom, was accurately located and sunk to the desired depth. New sections were added as the cutting edge knifed its way down through the overburden. It was then filled with concrete by the same method used in construction of Pier 17. On top of the solid steel and concrete caisson, main tower pedestals rise 25 feet above the water, their tops studded with steel bolts. Thick base plates were fitted over the projecting fingers of steel. A wetting, joining the concrete substructure and the steel superstructure into a permanent union, to have and to hold from this day forward. On July 2nd, 1955, American Bridge began the gigantic task of erecting the steel superstructure of the world's longest suspension bridge. A floating derrick erected the lower sections of each tower as far as it could reach. Then it helped erect a creeper derrick, which took over where the floating derrick left off. Clinging to the side of the tower, it worked its way upward like an inchworm. But there, the resemblance ends. For this fellow had a straight-up climb of over 1/10 of a mile, lifting steel sections weighing up to 80 tons in the process. The struts which tie the tower legs together were built up of sturdy steel box sections, assuring absolute tower stability. 5 months and 13,000 tons later, these creeper derricks topped out towers reaching 552 feet above the water, almost the identical height of the Washington Monument. Then, for an encore, the creepers erected the huge guy derricks on top of the towers, ready for the next phase of construction. And there they stood, lonely sentinels in the middle of the stormy straits. Lonely, yes, and sturdy too, for they were soon to withstand one of the highest winds ever recorded in the area. To jump the gun on winter and be all set for spring work, the two giant backstay spans were completely assembled on shore, floated to the site, and then carefully maneuvered into position. The long spans were slowly coaxed onto their final positions atop the piers and pinned into place. Just in time, too, for the very next day, blustering winter weather arrived. Work on the bridge stopped until spring. Meanwhile, thousands of deer hunters, backed up for miles in the Upper Peninsula, waited through many chilly, uncomfortable hours. Some with their hunting trophies, others with nothing more to show for their efforts than discouragement and cold feet, impatient for a place on the ferries, which were crawling slowly back and forth across the straits, while still more cars pile up. Not all operations stopped for winter. The flow of steel from American Bridge fabricating plants continued. Storing, sorting, assembling. Logistics, they call it, so that when the weather broke, bridgemen could reach for and find each piece of steel as they needed it. And then spring 1956 came to the Straits of Mackinac. After the guy derricks limbered their joints, stiffened by the wintry blasts, they were ready for the most spectacular phase of suspension bridge construction. Building the giant cables from the thousands of miles of steel wire shipped from the American Steel and Wire Trenton plant. After the wire ropes that were to support the catwalks were suspended to the exact curvature, this special decking, made of timber and cyclone fencing, was hung in accordion-pleated bundles until pulled down along the wire ropes with an assist from the bridgeman. While that trampoline performance, hundreds of feet up, seems to be a display of gymnastic skills, it actually served to speed the spreading of the catwalk. These bridgemen are perfectly at home on their sidewalk in the sky. On July 13th, a handshake marked the completion of the catwalks. With the catwalk secured against the wind, two tramway systems were erected on which the cable spinning wheels would shuttle back and forth between the anchorages. The reels of wire on the anchorages began to roll. First, up through the spinning tower to keep the tension on the wires just right for the spinning operation. With a clang of cowbells warning of their approach, the spinning wheels passed each other in the exact center of the bridge, depositing 8 wires, with each 3¼ mile round trip between anchorages. Each round trip took about 1/2 hour. The wires were looped over the strand shoes at both ends of the bridge, like a hank of yarn held between 2 hands. This was a job requiring precision, coordination, skill, and speed. But always there was the battle against time. 340 wires were to be banded into a single strand. Then, in a predetermined order, 37 strands were to be assembled into a single cable. 300 men, paired off in 2 shifts, challenged each other to friendly competition with no holds barred. Who could lay the most wire in an 8-hour shift? 30 trips of the wheel were par for the course. The winning crew boasted a record of 32 trips. Those 300 friendly competitors converted 41,000 miles of steel wire into 2 enormous 24.5-inch diameter cables in only 78 days. Hydraulic jacks put the big squeeze on the cables, and temporary steel bands were installed at 3-foot intervals. Then the permanent cable bands were installed. Even during the April to November building season, there were days when no one could work on the bridge. And then, another winter, another hunting season, more hunters, lucky and unlucky, with the long annual wait. Chins up, men. Next year, it'll be different. The ice moved out, heralding spring 1957. The bridgemen returned to their lofty perches. Down below and right on time were the reels of suspender ropes which had previously been used to support the catwalks. They had been removed, and during the winter they were stretched, cut into exact lengths, and socketed. A dual use of materials, one of many cost-saving procedures employed by economy-minded American bridge engineers. 368 of these suspender ropes were required. They were draped over their respective cable bands, where they dangled until they received their sections of the roadway. These sections were assembled on a dock at St. Ignace, then wheeled down a track onto waiting barges and floated to the bridge site. Installing the roadway sections was another fascinating operation that set this bridge apart. 89 of these sections were required to form the suspended roadway. Since the true parabolic arc of neither the cables nor the roadway would materialize until the full load of the roadway was suspended, the individual sections were not yet in proper alignment when they were raised. Thus, they were merely bolted loosely together until each later fell into place when new sections were added. The exact moment when each section moved into proper alignment was known in advance by engineers who had precisely plotted the entire sequence on electronic computers. For instance, when section number 30 was raised into place, sections 43 and 51, each hundreds of feet away, came into alignment and were then permanently fastened with high-strength bolts. It took a lot more than the longest suspension bridge in the world to cross the Straits of Mackinac. Actually, the north and south approaches together are longer than the suspended portion. When you consider that the extensive approaches are, in reality, a series of bridges in themselves, bridges long enough to span many important rivers, then the true magnitude of this part of the job becomes significant. Steel work on the approaches began on April 24, 1956, and was completed early the following year. Quite a feat in itself. All field connections, except those on the main towers, were made with high-strength steel bolts. The biggest job yet for this modern method of connecting steel to steel. Now we come to the last major phase in building this great bridge. The installation of the 7,400-foot-long bridge floor, 4 lanes wide. It, too, is revolutionary in concept. For each pound of material that goes into a suspended roadway, several pounds of steel are required in the structure that supports the roadway. So a special steel grid flooring, I-beam lock, was used to eliminate over 8,000 tons of dead weight, to more than cut in half the weight of a conventional roadway. Open flooring was used for the 2 inner lanes and center mall, not only to eliminate weight, but to achieve aerodynamic stability by giving the winds easy passage. This also lets snow and sleet through to give motorists a safe driving surface during the severe Mackinac winters. Additional weight was saved on the 2 outer lanes, even though the steel grating was filled with concrete, which was later crowned with a layer of asphalt. And one last benefit. This light flooring speeded up installation and was an important factor in the completion of the record-breaking construction schedule. When the roadway was completed, the main cables had taken on their permanent load and were generously coated with red lead paste. Then an ingenious machine neatly wrapped the cable with a tight protective coating of galvanized wire. Crossing the Straits of Mackinac by ferry averaged about 2 hours, including waiting time. During rush seasons, however, there have been waiting periods as long as 19 hours, with cars backed up as far as 17 miles. Under ideal conditions, ferries could handle only 462 cars per hour. Then, November 1st, 1957, the culmination of a 70-year dream, exactly on schedule. The joining of two halves of a state by the world's longest suspension bridge, spanning the Straits of Mackinac, destined to take its place among the great engineering feats of modern man. 5 miles in length, including its approaches. 19,205 feet of steel construction. 8,614 feet between anchorages. Hundreds of men setting new erection and safety records while working 2 shifts for 42 months. Pouring 440,000 cubic yards of concrete. Erecting 67,000 tons of steel superstructure to build a bridge with a capacity of 6,000 cars an hour. A bridge that reduced crossing time from hours to minutes. But these are merely cold statistics. This graceful and inspiring structure, combining strength and beauty, is another stepping stone in our country's growth. Here is an awesome and enduring monument to the science of bridge building. Here is a triumph of men and materials which forges another vital link in America's expanding highway system and defense plans. A tribute to the far-sighted officials of the great state of Michigan. A tribute to the deep foundation men, and a tribute to the men who forged the steel and linked it piece by piece, all working together to bring a bridge engineer's mathematics to life.